In Module 4, we're going to go into a deeper dive on variables and operators. A lot of this builds on what we talked about in Module 2 and just goes into a lot more depth. So let's get started. In this module, we're going to focus on some of the additional ways of creating and customizing variables, our own variable types, and looking at collections of variable types. And then we're going to look at extending the collection of available operators that are available in C by creating our own. So to get started, recall we already had a module talking about variables. We focused primarily on the primitive variable types that are built into the C language, our integer types and our floating point types. There's a lot more that we can do than what's already provided in the C language. So let's start and look at what we can do if we want to create our own variable types or collections of variable types, essentially leading up to custom data structures. So we're going to start with a short module, Module 4.0, on custom variable types. One of the ways of creating custom variable types in C is to create what's called an enumeration. So an enumeration essentially is a special case of an integer variable type that usually takes a very small fixed set of values. So recall, C already has different integer types for storing variables with different ranges, the smallest of which is an 8-bit value, which means it can store 256 different types. What if we want to create a variable with 2 different values or 10 different values? We can actually do that with an enumeration. So an enumeration is nothing other than a list of names that we can create to refer to this fixed set of values. And I think the best example of this is if we wanted to create a Boolean variable. A Boolean variable takes 2 values. They have names. They are false and true. We can use an enumeration to create a new variable type called a Boolean, and we can actually name the potential values false and true. Similarly, we could create a variable to keep track of the days of the week, Monday through Sunday, and we could refer to them by their names Monday through Sunday, and we could have a variable type that only takes those 7 values. So we do this using the enum keyword, which is just short for enumeration. And the enum keyword basically says we're going to define a new integer variable type, and here's its name. And here is a list of the values here is a list of the names of the values that it can take. So these last 2 lines are exactly definitions of enumerations. The first is a definition of the Boolean enumeration that can take values false and can take values with names false and true. And the second is an enumeration for a variable called day that can take values with names mon, Tues, Wed, Thurs, Fri, Sat, and Sun, representing the 7 days of the week. Now, like I said, these aren't actually the values of the variables, they're names for the values of the variables. And so where the enumeration keyword comes into play is what's actually happening under the hood is the compiler is creating a collection of integer variables with the given names. In the case of Boolean, it's creating a variable called false. It's creating a variable called true. It's assigning the value 0 to false and the value 1 to true. For no reason other than 0 is first and 1 comes next. So it's enumerating a list of variables starting with the value 0 because it's a good default place to start. It turns out you don't have to start with the value 0. You can start anywhere you want, and in fact, you can specify the default starting value. So in this case, I've taken those first 2 lines of code, I've made one tiny change. The tiny change I've made is I've specified the value of Monday is 7 for no reason at all. I just wanted to pick something other than 0. So now I have enum boolean false true, enum day starting with mon equals 7 and enumerating the rest of the days of the week. So now these are nothing other than custom types. These are the variable names. The values are created as part of the enumeration. Again, the value of false is going to be 0. The value of true is going to be 1 because that's how the enumeration is created. The type includes the enum keyword as well as the name of the enumeration. So now if I want to create a Boolean variable, its type is enum Boolean. And I can create a Boolean variable with a name x, and I can assign it the value of false. The value of false is actually 0 because of how the enumeration was created. So through this definition, I've essentially defined an integer with a value of 0. But there's nothing here that says either integer or 0. So this is an abstraction. This is an abstraction that says I have a variable that only takes 2 valid values, 0 and 1. I don't care that there's 0 and 1. I can call them false and true. The enumeration defined them as 0 and 1. I don't care. Similarly, I can say I want to declare a new day. I want to call it today, and we'll say today is Wednesday. Nowhere in this line of code did I indicate that this is an integer with a value of 9. But in reality, this is just an integer with a value of 9. And now I can operate on these variables just like I would any custom variable with custom values. And I can do things like conditional logic, like if today plus 1 is greater than or equal to Friday. Well, if we really think about this, today plus 1 being greater than or equal to Friday, Monday is 7, Tuesday is 8, Wednesday is 9, Thursday is 10, Friday is 11, so on, so on. The only days that are greater than or equal to Friday are Friday, Saturday, and Sunday. So if today plus 1 is at least Friday, that means today is at least Thursday, that means it's almost the weekend. So I can think through sort of logically thinking about this in terms of days of the week. I don't have to care about Friday is 11, today is 9, what's 9, what's 11, when's the weekend. I can make this nice abstraction. So an enumeration is nothing other than a nice abstraction with named variables, with named values. And this becomes really nice when you have, say, for example, a list of values that you care about, a list of potential error codes that can occur, a list of potential values that a piece of hardware can create. These become very nice custom ways, and then we never have to deal with the scenario of this variable taking a value outside of that range, because this variable can never take a value outside of this range. The value of this Boolean x can never be 3. The value of today can never be 47. It's not allowed because the enumeration doesn't provide for it. So another thing that we can do in terms of creating our own custom types is we can do what's called a type definition. Now, a type definition is an instruction included in C that allows us to create an alias. And so a new type is nothing other than an alias for something constructed using existing types. And this is usually, again, just another nice abstraction. It's a nice way of simplifying code that allows us to use shorter aliases for things that already exist. Now, in C, the way we do a type definition is we use the typedef keyword. And the way we use the typedef keyword is we say typedef, we give an existing type, and then we give the alias. So let's say, for example, I'm going to be doing a lot of programming with unsigned long integers. And I'm going to be doing that because I'm going to be referring to a lot of memory addresses. Well, typing unsigned long is a lot of characters. I can, and if I'm doing this purely for memory addresses, maybe I can just create a type def called memaddress. So here, this line of code will do exactly this. Type def unsigned long mem underscore addr will create a new type called memaddr, and that type is exactly unsigned long. So now instead of typing unsigned long in my code hundreds and hundreds of times, I can type memadder, and I know that this means it's a memory address. Memory addresses can never be negative, they're always long. I could also do things like I just created this Boolean enumeration, and instead of needing to say enum Boolean every time, I can type def it into something nice like bool. Bool is exactly what's defined in the standard Boolean library, and this is in fact how it's defined. They create an enumeration that supports two types, false and true, with values 0 and 1. They use a type def to create the type bool. If we do this once, as a definition in our code, create our enumeration, now to create a new Boolean variable, bool b. That's it. We don't need to write enum every time. And of course, as our data types get more and more complex, this type def becomes more and more valuable. And we'll see this relatively soon. So let's go into module 4.1. Module 4.1 talks about arrays. And in particular, we're going to start with what are called static arrays. So here, instead of talking about new types, we're talking about collections. So a static array is essentially a collection of variables of the same type. So for example, I want to keep track of a list of integers, a collection of integers that are ordered. This is a list. The word static here means that the size of the collection is fixed and the resources used to store the collection are fixed. And these are determined at compile time. The values that are stored in the array can change, just like any variable, any non-constant variable. But the array itself is going to be fixed. To create an array of a particular type of variable, we use the index operator or the subscript operator. Some people call this the square brackets operator. And we can declare arrays in a number of different ways. So let's say, for example, I want to create a list of integers of length 5. And I want to call that list values. I have 5 values that I want to store. I can define that array by saying int values index operator of 5. This means I'm declaring a list of integers of length 5. That the name of that list is values. If I want to assign initial numerical values to my list values, I can do that using the curly brace list notation, similar to how we defined an enum type. If I give a list of 5 values, I actually don't need to say that the array is of length 5. I can, but I can remove that 5 because now I'm giving 5 values. It knows the array is of length 5. So now it's not only I want to declare a list of integers called values, I want to declare a list of integers called values containing the values 0, 1, 2, 3, and 4 in that order. If I want all of my values to be the same, I can give the length and one value in the curly braces notation, and it will copy that value into every entry of this list of length 5. So here I've given 5 unique values, which will determine the length is 5. Here I give 1 unique value, but I tell it the length is 5. That gives me 5 copies of that value. These are all ways of creating a static array at compile time in C code. Now, once we have an array, the array itself has the name values that we've given. Each individual entry in the list, we use the index or the subscript operator. So if I want just the first entry of this array, the name of that variable is values indexed at 0, sometimes called values of 0. So the 5 entries in my array are values of 0 through values of 4. And we can use these just like any other integer variable, because in fact these are just integer variables. So a simple example of using static arrays, I can declare an array, 2 arrays of length 10. One is named squares, one is named cubes. Both have length 10. I'm simply going to populate them with the squares and the cubes of the numbers from 0 through 9. Squares of 0 is going to be 0. Cubes of 0 is going to be 0. Squares of 1 is going to be 1. Cubes of 1 is going to be 1. Squares of 9 is going to be 81. Cubes of 9 is going to be 729. So this is simply populating a list with a sequence of numbers. And these numbers are all related to each other. It's a sequence of squares, a sequence of cubes. So it makes sense to have a collection rather than needing to store 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, and so on. As the length of the array gets very long, that would be a lot of variables that we're creating. This collection allows us to create that in a very compact way. Now, a special type of static array is a static array made up of characters. And it turns out these are very, very useful because they are strings. A string is nothing other than a static array of characters with a caveat. A string actually in nearly all cases needs to be a static array of characters ending with the character 0. This is called a null terminated array of characters. In the ASCII encoding, a null character is actually indicated by /0. In ASCII in /0. Numerically, it has a value of 0. So you can either think of this as the integer 0 or the ASCII character of null. But in any case, when we define a character array, we can do that by simply giving it a string. So in this case, if we give it a string literal, which is a constant fixed string, meaning characters in quotation marks, we can initialize a character array using that string literal, and it will actually be the same as defining that as the characters A, N, D, R, E, W, and a null character. And then the special thing with strings that we can do is they're a sort of special type in C. So if we're doing things like printing the contents of a character array, we can say that is a string. We don't have to print them character by character and loop through. We can say print the string, and the printf function knows, as long as there is a null character at the end, it knows to keep printing everything up till but not including that null character. So if we run this code, we tell it first name is Andrew, last name is Carnegie, and I do printf first name space last name new character. If I actually were to go and run this code, let's see, if this is here, it prints for me. This is exactly that code. Exactly that code, where it knows, because the null character is at the end, it knows where the string ends. This becomes important for a lot of reasons later. So it prints the contents of the first string, the space, the contents of the second string. It doesn't print any of the null characters, and then it prints a new line. And we can see that's exactly what shows up here on our terminal when we run that program. So, strings are very useful. And if we end up doing a lot of things with strings, it turns out there's an entire library for handling strings, for assigning values. But for now, we can treat static strings just like arrays. I could actually go in to this first name variable, and I could, for example, set first name of 5 to S. And if I do that, I have changed the name Andrew to the name Andres. And I can do that by using standard array operations. First name of 5 equals single quote character S. That is a valid thing to do. So strings are not fixed. They're mutable. They can be changed. They can be modified. The individual characters can be changed just using standard array indexing. Now we can do more interesting things. Any type of variable can be turned into an array, which means an array can be turned into an array. So this is another example. I have a list of numbers, 101, 001, 110, and I'm telling the system to create an array of length 3 of integer arrays, an integer array of arrays of length 3. So this is going to say, okay, there are 9 integers. You want an array of arrays of length 3. That means this outside array is also going to have length 3, because that's how much data you gave me. That the compiler knows how to handle that. It knows that this is essentially creating a 3x3 table or a 3x3 matrix. So what this code is doing now is in one line of code, it's creating a 3x3 two-dimensional array, or a 3x3 matrix, populating that matrix with values, all in one line of code. These other lines of code are going through and printing that array. So again, we can go and look at how this works. I have the multi-dimensional array code. It is exactly this code from the slide. We can compile that code. And when we run this, what we expect to see is we expect to see the printed out version of our 3x3 array. And in fact, that's exactly what we see. So the array was created and populated all in that one command. Everything else in this code is just to print that in a nice 3x3 output with some spacing and some new lines and make it look nice and pretty. Now, if we look at the way this was populated, 101, 001, 110, we can go back and we can see 110, 001, 110. What this did is it simply loaded arrays of length 3, take the first array of length 3, put it at M0, take the next array of length 3, put it at M1, take the next array of length 3, put it at M2. So that's how the compiler is processing that data and creating that multidimensional array. And in general, as long as the number I give here is an equal divisor of the amount of data that I'm giving here, this will work. I could have put a 3 here. That would have worked just fine. But I don't need to because the compiler knows I gave it 9 values. All right. So other things that we can do with arrays, and particularly with strings. We can use the size of operator. If you recall the size of operator that we talked about in module 2, it tells us how much memory a variable is using in the system. We can use this operator with static arrays. So in particular, if we create a string as an example of a static array, we can then go in and say, tell me how much memory this string is using. And in this case, if we create our first name of Andrew and we tell it to print the size of that first name, it's going to tell us that the length or the amount of memory is 7 bytes. And that makes sense because we saw earlier that when we create a static string, we have each character and then we have the null termination character at the end. So including the null termination character, we have 6 characters in the name Andrew, the null termination character, which gives us 7 bytes because each character is 1 byte. This is exactly what we expect. We can go a little bit farther and we can say if we go in with our multidimensional array example, our 3x3 matrix that we defined before, we can use the size of operator there as well. We can say how much memory is used to store that entire 3x3 matrix. And in this case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 integers. Each integer is 4 bytes because the size of an integer on our system is 4 bytes. This takes 36 bytes. And in fact, if we print the size of m, where m is a 3 by 3 two-dimensional static array, it will take up 36 bytes of memory. We can also print m of 0, which is going to be one row of our matrix. One row of our matrix, 3 by 3 matrix, contains 3 integers. M0 in particular stores 101. Each of those is 4 bytes. So this is going to print 12 bytes. And this is exactly what it does, as we expect. We could do the same thing to actually learn if we have a multidimensional array, static multidimensional array. We can then figure out the number of rows and the number of columns programmatically. So if we wanted to do something like, say, thank you for entering a 3 by 3 array, we could learn by doing some simple manipulation, some simple math, that there are 3 rows and 3 columns in our array. Size of m divided by size of m0 turns out to be the number of rows. Size of m0 divided by size of an integer or size of m00 is the number of columns, 3. So we can programmatically get the number of rows and the number of columns for our array. This ends up being a nice little construct that we'll come back to and use again at a later time. All right, so that's as much as I wanted to go into with arrays. They're relatively simple. Static arrays are pretty easy to use, nice things to have, in addition to enumerations and type defs. Now we can start to get into more complex collections of data, and so we're going to move from arrays on to data structures.